In this video, we'll look at a couple of concepts related to angles. So the first is one that you may remember from high school, but might not. So if I have an angle, and so I'll just draw kind of a random angle here, um, then there are two angles that are related to it that are very special. So the angle that I'm going to be working with here is the red angle, and I'll call this alpha. And then the two very special ones that are going to be related is this angle here, which I'll call beta, and this green angle, excuse me, the green angle, which goes like beta does, but all the way around to the horizontal. So if alpha is our angle, then the two angles that go with it, beta and I suppose I should give the other one a name, gamma, are called the complement and the supplement respectively. So the complement is in this case beta, and the supplement is the angle gamma. Okay, now how do I calculate these? Well, the complement is whatever angle alpha and beta, or whatever angle beta needs to be so that alpha plus beta is 90. So the definition of the complement is this. Now, it doesn't make sense to do this if alpha is itself bigger than 90 so that beta would be negative. So you only actually can talk about the complement in any sort of sensible way if the angle alpha is acute, so less than 90 degrees. So similarly, the supplement you get by looking at what angle does alpha need to add to get 180 degrees, which is the sort of measurement of the straight line down here. So here we need alpha plus gamma to equal 180 degrees. Okay, so let's look at a quick numerical example. So let's say that I have angle 59 degrees. Then the complement is whatever angle 59 degrees plus some beta equals 90. And so this is pretty easy to solve for beta. Just subtract the 59 over, and we end up, or just do it in your head, and so we end up getting that beta is 31 degrees, and that's the complement. The supplement is whatever you get, or whatever you need to add up to 180 degrees. So here we'd have 59 degrees plus gamma equals 180 degrees, and then gamma would be just, let's subtract the 59 over, and so what should we get here? So it'll be 180 degrees minus 59 degrees, which would be 121 degrees. Now, you may have noticed sort of a fact here from the pictures, namely that notice that the supplement is 90 degrees more than the complement, and that should kind of make sense based on the picture, because these two pieces here add up to 90, and so if you take the supplement and you add up 90, then you get the, or sorry, the 90 to the complement, you get the supplement. Okay, so in the next segment we'll look at another way of measuring angles, and that's degrees, minutes, and seconds. So this isn't particularly difficult, but well, partly because the word minute and second will kind of be the giveaway as to how to work with this. So sometimes angles are measured in a form that has both minutes and seconds. So you could have, say, for example, 130 134 degrees and 40 minutes. And this is sort of an alternative way of describing angles instead of saying something like 130.5 degrees or whatever. The idea of minutes here should sort of conjure up an idea of time. So in the same way that there are 60 minutes in an hour, there are 60 minutes in 1 degree. And you could further subdivide the minutes into, not surprisingly, seconds, and 60 of those equals 1 minute, and hence 3,600 seconds is the same as 1 degree. Okay, so let's convert something between these two measurement systems. So let's take the 134 degrees and 40 minutes. So the way that you convert this to just plain old degrees is the degree part is easy. 134 degrees, 40 minutes is 134 degrees plus some stuff. And the stuff, well, if 40 minutes is what we've got, and 60 minutes is equal to 1 degree, then you can kind of approach this like you would a unit conversion problem in science. So we'll have 40 minutes times, well, 1 degree is 60 minutes, and then we just need to kind of multiply everything out. So 60, minutes, not seconds. So 60 minutes, and then the minutes will cancel and we'll be left with something in degrees. And so in this case we get 134 degrees plus 40 over 60 is the same as 2 over 3 degrees. And so as a decimal, this would be 134.66 degrees roughly. It's actually 0.66 repeating and so on. So let's just put that here, 0.6 repeating degrees, because 2/3 is 0.66. So what we can see from this is that the 134 degrees 40 minutes is close to 135 degrees, and it's 2/3, and the 2/3 isn't perhaps too big of a surprise because of the idea of the 40 minutes. In this section, we'll look at the idea of arc length. So if we have a circle, I'll just draw one here, and if I cut off an arc of this circle by means of two straight lines, so I'll put one of them here on the positive x-axis and then another one, say, up there like that, then the arc of the circle is the piece that I'm going to sort of color over in blue. And the angle that relates to that is this angle here in between the two line segments. So the arc of the circle has the central angle alpha. Okay, so whatever angle in here sort of cuts off that arc, that we'll call the central angle. Now there's one other obvious piece of information that we need in order to describe this circle. We need to know how big it is. So we need to know whatever the radius of this circle is. And so what we're going to do here is come up with a relationship between this length, the stuff in blue, which for some reason we use S for arc length. So S is the arc length, because arc length, of course, totally has the letter S in it. So the formula that relates these three things together is actually pretty simple. So the arc length is just the radius times the angle. Now there's one big caveat here. The angle must be in radians. So you get garbage answers if you use the angle in degrees. So if we're given an angle in degrees, we'll need to first convert it to radians. Now the nice thing about this equation is that you can be given any two pieces of the information or two pieces of information about the triangle and, or excuse me, the arc, and you can find the other one because you've got 2/3 of the things in this formula here. So let's look at a quick simple example. So let's say that we have a um, a circle, and its radius is 36 centimeters, and the angle, the central angle, is 30 degrees. Okay, so we'll kind of just sketch a picture. Actually, the picture I've got here, here the angle alpha is probably something like 45 degrees, so we'll need something a little smaller than that. So say something like we've got our angle here. Oops. So I'll draw the x-axis there, and then 30 degrees is something like about here, roughly. And so we know that the radius in this case is 36 centimeters, and this angle is 30 degrees, and we're interested in what the arc length there is, s. So there's one immediate problem, namely the angle here is given in degrees. So let's convert 30 degrees into radians. So the way you convert that, of course, is just 30 degrees times, there are pi radians for every 180 degrees, and so if you just cancel the radians, and 30 over 180 is a sixth, so you just get pi over 6, and that's our radian measure. Okay, so now that we've got the angle in radians, we can use our formula that the arc is equal to the radius times whatever the central angle is. In this case, we'll call it theta. And we know the radius, it's 36 centimeters, and we know the angle, it's pi 6th radians, not the 30 degrees, even though those are the same angle. So our arc here is 36 times pi over 6. Of course, you can cancel 36 over 6 is 6, and so we get 6 pi centimeters. Now, this answer may seem a bit unsatisfying because, of course, pi isn't a nice number, so we can approximate this knowing that pi is about 3.14 or so, and if you do that to 2 decimal places, you get about 18.85 centimeters. So that seems relatively reasonable. 30 degrees, well, maybe not in my picture here, but hopefully you get the idea.